Okay students, in our last lecture we have seen the different methods to determine the order of reaction, in which we discuss the 5 different methods. In our today's lecture we consider the very important term, that is effect of temperature on rate of reaction, which includes the basic concept of energy of activation. In our previous lecture we have discussed the effect of temperature and concluded that when temperature of any reaction system increases, the reaction rate also found to be increases, which can be accounted on the basis of reaction rate constant. That is, here the Van 't Hoff rule explains it. Gamma raised to n equal to k T plus n times 10 upon kt, where n is positive or negative or maybe fractional. It is a simple number. It does not reflect the order of reaction. It is the simplest number which may be positive, negative or fractional. K is reaction rate constant and T is absolute temperature. So when temperature increases, the rate of reaction increases, because the reaction rate constant increases. If you imagine the reaction rate law equation, it contains the rate constant and the concentration terms of reactants raised to appropriate number or powers or exponents. So here this ratio of reactant rate constants at a higher temperature to the lower temperature gives us the temperature coefficient with respect to the increase in the rate of reaction. This energy of activation term, this diagram reflects the energy profile diagram in which the potential energy is plotted on y-axis and the progress of reaction is plotted on x-axis. Progress means initially the reactants are there and after completion of the reaction the products are there, and in between the reactant and products, how the reaction proceeds, that is given in terms of progress of reaction. So here we consider the energy of reactants here, ER. In this diagram it is higher than that of energy of products. Here the products are there and the corresponding value of energy is EP, energy of product. Here the reactant is there, the corresponding value of energy is ER, that is the energy of reactant. And here a peak is there and the corresponding value of energy is E suffix T, small t, and that is here threshold energy. And the difference between this threshold energy and the energy of reactant is known as the activation energy, EA, activation energy. So activation energy is the difference between threshold energy and energy of reactants. And if we consider here the difference between EP and ER is delta E here, energy of reaction. It may be represented by delta E or may be represented by delta H, that is heat of reaction or energy of reaction. So here this energy of reaction, if we consider, then energy of reactant is higher, that of product is smaller. So delta E is E2 minus E1, E2 means EP, E1 means ER, and here this value gives you negative. Delta E or delta H here is negative. So this is the diagram for exothermic reaction. Energy of reactants is higher and energy of products is less. So some part of energy is given out from the system, and that's why it becomes here negative here. Delta E becomes here negative. And here some amount of energy that the reactants should absorb go to the highest value here, peak value, and thereafter the small disturbances roll towards the product side. So this is the minimum amount of energy that the reactant molecules must absorb before they could react, and it is denoted by EA, and it is known as energy of. Now this energy of activation can be understood from the Arrhenius equation. This is the form of Arrhenius equation which can be considered on the basis of want of reaction isotherm. So it relates the equilibrium constant, capital K, equilibrium constant. R is universal gas constant. T is absolute temperature. And delta H or delta E is change in enthalpy. Here, delta H or delta E is change in enthalpy or change in internal energy. So this particular equation can be converted into two forms. Two forms of Arrhenius equations are there. This form is known as differential form, and this form is known as exponential form. So in the want of reaction isochore, equilibrium constant is related towards the temperature, while the Arrhenius equation relates the reaction rate constant, small k. Here it is capital K, equilibrium constant. Here it is small k, reaction rate constant, and energy of activation and that of temperature. So reaction rate constant and temperature, they are related with each other by using the Arrhenius equation. The two forms are there. One is the differential form, d upon dt, and one is the exponential form, means k is given in terms of e raised to minus e upon RT. Now we consider in short the proof of Arrhenius equation, how it can be obtained. Let us consider the form of want of isochore, dln capital K by dt equal to delta H upon RT square. Equilibrium constant can be given by K1 upon K2, that is the rate of forward reaction rate constant here considered, to that of reaction rate constant of backward reaction. That's why the equilibrium will be get established between reactants and products, and therefore here the equilibrium constant. K will be replaced by K1 upon K2. And here delta H will be replaced by delta E, internal energy, rather than the enthalpy. Okay, we split this equation into two equations. One that for forward reaction K1 and one that for backward reaction K2. So these two forms that we obtain, here we consider equilibrium constant and here we consider the reaction rate constant. So this form of equation is represented in general as d ln k by dt equal to E upon RT square. E upon RT square. This is the one form of the equation that we get, is the differential form of the Arrhenius equation. Here E is the energy of activation and the logarithmic form of it can be represented in the form as, and this one can obtain by integrating this equation. Integrating this equation from initial temperature T1 to final temperature T2, the corresponding value of reaction rate constant at lower temperature is K1 and at higher temperature is K2. So we write this equation in the form as d ln k integration from K1 to K2 equal to integration of E upon RT square into dt. Okay, so we shift this form of the equation and integrate, and we can obtain this form of equation. Okay, we can obtain this form of equation. Integration and differentiation here get cancelled. So only ln k, this is the natural logarithm. If we convert this to the log to the base 10, so a 2.303 term will be included in this logarithmic form of the Arrhenius equation, which explains how the reaction rate constant and or rate of reaction is related towards temperature, because the reaction rate constant is nothing but rate. Reaction rate constant is nothing but a rate of reaction when the concentrations of all the reactants is considered or assumed to be unity, and that's why reaction rate constant can be considered in terms of rate of reaction, and that's why rate or reaction rate constant, they are here found related with the temperature. With the increase in temperature, how the rate of reaction changes, that can be given by these logarithmic form of the equations here. We consider how this energy of activation will be estimated or determined. There are two methods. One is the graphical method and another is the analytical method. In the graphical method, we consider the exponential form of the equation. Exponential form of the equation. And we rearrange this exponential form of this equation, Arrhenius equation, in this form. ln k equal to minus E upon RT plus ln A. And this is the form of equation as y is equal to mx plus c. So ln k as a y, so we plot this ln k on y-axis. 1 upon t as a x from this. So we plot 1 upon t here on x-axis. So y is equal to mx. So m can be compared to minus E upon r. M is slope. Minus E upon r. Slope is negative. That's why the nature of the plot is of this fashion. Declined fashion. Okay. And here the intercept on y-axis gives you the value of ln A, where A is the pre-exponential factor from the exponential form of the Arrhenius equation, or it is also called as Arrhenius constant. So this Arrhenius constant capital A or pre-exponential factor can be obtained from this plot, and from this slope we can obtain the energy of activation. What is the slope? Slope is dy by dx. So y2 minus y1 divided by x2 minus x1 gives you the value of slope, that is negative. So negative slope, and this negative number, it becomes negative, negative, positive, and you can obtain the value of energy of activation. So the value of energy of activation means the minimum amount of energy that the reactant molecules must absorb before they could react, can be evaluated from this graphical method. It is one of the important. And the second method is known as analytical method. In the analytical method, we use the form of equation log of K2 upon K1 equal to EA upon 2.303 R into bracket T2 minus T1 divided by T1 T2. We carry out the experiment of the, suppose, hydrolysis of an ester. We have performed this experiment at our T.Y.BSc practical course, and in this T.Y.BSc practical course also we had it. So we consider this experiment in the practical course, and we are repeating the experimental set at the one of the room temperature, we call it as T1, and one of the higher temperature T2, that is approximately higher by 10 degrees Celsius. So T1 is lower temperature and T2 is higher temperature of the system. And by evaluating the values of K1 for lower temperature and K2 at higher temperature, we obtain the values now of K1 and K2 from experimental sets. We know T1 and T2. We know the universal gas constant. Substituting the values K1, K2, T1, T2, absolute temperatures here means the degree Celsius temperature plus 273, that can be considered here. So T1, T2, here T1, T2, here product is there, here difference is there, universal gas constant. These values are known from the experimental sets. So energy of activation can be determined. So this energy of activation is very important concept, and that could be understood from the energy profile diagram that we have initially seen, and in which some cases we found the exothermic reactions, some cases of reactions that we found endothermic reactions. It means in endothermic reactions energy is absorbed. It means the energy of products is somewhat higher than that of energy of reactants. And from such conditions, whether the energy of activation is smaller or greater can be judged from energy profile diagram. If energy of activation is smaller, the reactions are faster, and if energy of activation is greater, then the reactions are comparatively slow. So this is the very important concept of energy of activation that we accounted in the chemical kinetics chapter. Now, on the basis of the different equations like this logarithmic form or the exponential form of energy of activation, or that of the Arrhenius equation, or the reaction rate constant values for third order reactions, or that for determination of order equations from half-life or from the rate method, or that for the reaction rate constant for third order reaction, or the half-lives, the different parameters can be evaluated here. So please try to do as a assignment that to evaluate the reaction rate constants, energy of activations, half-life periods, knowing the half-life, reaction rate constants, please do this as the assignment. So we end here as our first chapter, and that is the chemical kinetics. Now, if you have any problems about or any doubts about this chapter 1, you can communicate with me, and from next time we proceed for the next chapter, from the physical chemistry course, that is CH331. Thank you.